Here we'll learn an overview of blood pressure. To begin, start a table and denote that blood pressure is expressed as the difference or change in pressures between 2 points along a vessel. As the statement implies, blood pressure is not constant throughout the cardiovascular system. To show this, draw a pressure profile graph. On the y-axis, write pressure in millimeters of mercury. Write the values 0 to 120. Along the x-axis, write the key cardiovascular structures as follows. The left atrium and left ventricle, which are the chambers of the heart that pump oxygenated blood. The aorta, which is the largest artery in the body, it receives blood directly from the left ventricle. The large arteries, small arteries, and arterioles. The capillaries, which are where gas exchange occurs. The veins. The right atrium and ventricle, which receive deoxygenated blood from the body and send it to the lungs via the pulmonary arteries. Next, let's draw a curve to show two key principles of blood pressure. First, that it changes as blood moves throughout the body, and second, that it's pulsatile because of the rhythmic contractions of the heart during the cardiac cycle, which we discuss in detail elsewhere. In the left atrium, blood pressure is relatively low, at about 5 millimeters of mercury. It's much higher in the left ventricle and aorta, where it oscillates between 120 and 80 millimeters of mercury. Arterial pressure rises slightly as it passes through the large arteries, then begins to fall. Write that pressure drops significantly as blood moves through the arterioles because they're the site of highest resistance to blood flow. Within the capillary networks, blood pressure falls to about 4 millimeters of mercury by the time it reaches the venous system. Blood pressure remains low in the right atrium at about 4 to 6 millimeters of mercury and rises slightly in the right ventricle. Within the pulmonary arteries, blood pressure is around 2 to 4 millimeters of mercury. Recall that blood traveling through these vessels travels only a short distance to the lungs. The low blood pressure is sufficient for lung perfusion, but not so high as to cause damage. Indicate that the blood within the arterial system is the stressed volume. It's under high pressure. Conversely, the blood within the venous system is the unstressed volume, as it's under significantly less pressure. Also recall that the majority of the blood is within the venous, the unstressed portion of the circulatory system. Denote in our table that the pressure differences along the cardiovascular system provide the driving force for blood flow. Next, let's take a closer look at the pulsatile nature of blood pressure. Start a new graph to show the arterial pressure changes of a single cardiac cycle. Along the y-axis, write pressure, again in millimeters of mercury, write the values 80 and 120. Along the x-axis, write time. Next, draw a curve to show that the highest arterial pressure is 120 millimeters of mercury. It's reached during systole when the left ventricle contracts and blood is ejected to the aorta. The lowest pressure, 80 millimeters of mercury, is reached during diastole, the period of ventricular relaxation. Indicate the dichrotic notch, which reflects a temporary drop in pressure after systolic contraction. It's caused by the backflow of blood after the aortic valve closes. Clinically, blood pressure is usually reported as systolic pressure over diastolic pressure. 120 over 80 millimeters of mercury is considered to be a healthy blood pressure. Clinicians are also interested in the pulse pressure, which is equal to the systolic pressure minus the diastolic pressure. So if systolic pressure is 120 and diastolic pressure is 80, then the pulse pressure is 40. Write that pulse pressure is primarily determined by stroke volume, which is the volume of blood ejected from the left ventricle per beat, and arterial compliance, which reflects the ability of the vessel wall to contract or expand to accommodate changes in blood flow. Alternatively, mean arterial pressure, MAP, is equal to the diastolic pressure plus 1/3 of the pulse pressure. So if the blood pressure is 120/80, then the mean arterial pressure will be 93. Notice that mean arterial pressure is not simply the average of the systolic and diastolic pressures. The equation accounts for the fact that the period of diastole is longer than that of systole. Right, that mean arterial pressure is determined by cardiac output and peripheral arterial resistance, also referred to as systemic vascular resistance. In systemic shock, vascular resistance plummets, and so does the pulse pressure, so the body is poorly perfused. Finally, let's learn 3 arterial pressure gradients that physiologists are interested in. Write that the driving pressure gradient refers to the change in pressure between 2 points along the longitudinal axis of a vessel. Draw a vessel and show that blood flows unidirectionally through it. Indicate P1, or pressure at point 1, and P2, pressure at point 2. P1 minus P2 equals the change in pressure between the 2 points. This is the driving pressure. Driving pressure can refer to changes in the overall systemic cardiovascular system or simply within a single organ. For example, knowing the driving pressure of the kidneys is important for understanding renal function and pathology. The hydrostatic pressure gradient refers to the change in pressure between 2 points along the axis of a non-horizontal. For example, the femoral arteries, which deliver blood vertically from the heart to the lower extremities. Draw a vertically oriented vessel and write that H1 minus H2 equals the change in pressure as blood flows through the vessel. Be aware that this hydrostatic pressure is different from the hydrostatic pressure that regulates passage of water and solutes across capillary walls. Finally, write that the transmural pressure gradient is the change in pressure across the vessel wall. Draw a vessel and indicate the direction of blood flow. Then show that the blood inside the vessel exerts a force, R1, on the internal surface of the vessel wall, and an opposing force, R2, is exerted on the external surface of the vessel wall. This force comes from the surrounding tissues. Write that R1 minus R2 equals the change in pressure across the vessel wall. Transmural pressure is important because it influences vessel diameter and therefore resistance to blood flow. This concludes our diagram.